just had an introduction to what a GPU is at a very high level, at the very least, and some of the software technologies. But what's probably more interesting to a lot of you is how can I use GPUs at the NRIS systems, so Betsy or Saga, for instance. And that's what we will be talking about in this session. So I will do a boring PowerPoint presentation, and then Stig Rune will do a bit more of a hands-on in the terminal, so you will actually see how these commands actually run. But hopefully, PowerPoint presentation can be good so that you have something to look back on later, and they can look up resources, for instance. So I'll mention a little bit about what resources we have available at NRIS. We'll talk a little bit about the module system and how to find GPU optimized modules. We'll spend quite a bit of time talking about the batch system, so slurm, and the options that you have there for GPU. And lastly, I'll mention again how to get help, get in touch with us, all of that. And the last point here is not something that we'll talk about, but everything that I will be talking about today is documented at our documentation page. So if you haven't seen that before, please have a look there. And I especially recommend searching for GPU terms that you're interested in, and hopefully. And if you don't find what you're looking for, then please don't hesitate to contact us and send us support emails at support emails with the address support@nris.no. So we actually have two systems now with GPUs. We just got new GPU nodes on Betsy, but on Saga, we have had GPU nodes for quite some time now. There are 8 GPU nodes with 4 GPUs per node. Those are unfortunately a bit older P100 cards, but they're still actually quite performant. And in a lot of especially scientific compute tasks where you need float 64 support, these P100 cards are actually faster than the consumer or prosumer cards from NVIDIA. So we actually benchmark these P100 cards, and they are quicker than the 2000 series from NVIDIA. Not faster than the 3000 series, but those are again quite new and might be difficult to get your hands on. But that's all just to say that please don't shy away from using Saga for your GPU compute needs, especially for developing and stuff like that. On Betsy, as I just mentioned, we have gotten a new GPU partition. Currently, there are 4 GPU nodes, each with 4 NVIDIA A100 cards, 4 NVIDIA A100 cards per node, I should say. And these cards are connected by NVLink, and that's very nice to have if you're doing machine learning stuff, or if you can actually divide your compute across multiple GPUs, because then you don't need to actually go into system memory to communicate between the GPUs. So that's very nice to have. It's important, and we'll get back to that later as well. But Saga, you heard previously that you can just ask for a single CPU or a single task for a single CPU in Slurm terms. But Betsy is a bit of a different system, and for the normal compute partition, we actually you actually have to request a minimum of 4 full nodes, but that's not the case for the GPU nodes. So the GPU nodes on Betsy are handled differently than the rest of the Betsy cluster, and the GPU nodes on Betsy are actually much closer to Saga in the way that you ask for compute on them. So you're able to ask for a single GPU and a single CPU if that is all that you require. And I also want to implore you that if you feel that the GPU, the resources that we have available are not sufficient for your needs, please contact us. As we'll see later, we have one other system that we could help you get access to. And also, if we get more desire for more resources, we can also argue better for those expenses. So hopefully we can get more resources in the future. So what are the available modules in the module system? Well, I'm not going to list all of them because that will probably be too many, but I tried to isolate some of the tool chains that you should look for when looking for software. And the most important tool chains that you should look for is, of course, the CUDA tool chain. GCC CUDA is another tool chain, FOSS CUDA as well. And then lastly, PGI/NVHPC are also tool chains that indicate that there is some sort of GPU acceleration going on. So if you see CUDA in the name, then that means that the software is explicitly built against CUDA, and it's usually a very good sign for that software to be using GPUs. It should be quite easy. If you see GCC CUDA, that means that the software is built against GCC and CUDA. That tends to indicate that the software can optionally offload. So you will see a lot of the larger software packages, such as Gromacs and Gaussian, either have GCC or GCC CUDA as their toolchain, because both of these softwares are conditionally required to support CUDA. They don't have to have a GPU to actually function, but they can function with the GPU as well. And lastly, PGI NVHPC also usually indicates very good support for GPU offloading, but there aren't that many tool chains that use that at the moment on our systems, but it can be nice to know about all of these. So next time that you want to check the availability of a module, keep in mind these tool chains, and we'll quickly look at how that could look on our system. So let's say that you wanted to use OpenMPI for your application. And that is a software package that we know can conditionally work with CUDA. So you can have CUDA aware you can have CUDA aware MPI. And we actually have that on all of our systems. But how do you separate that from all of these? Well, as I said, think about these 4 or 5 main tool chains and try to identify them. So if we see in this list here, we can see that 2 of these packages are compiled either with PGI or GCC CUDA, which usually indicates that there is support for that. So an easy way to sort of look for that. We can go one further. Here I've checked for Gromacs, and we get a lot of different versions, different tool chains. But as we can see, there is one version there which supports CUDA offloading. I should say that we try to document this on our documentation pages. If for larger software packages, we have a separate page for the software packages where we document how to use them in the regular manner with slurm, our batch system. But we're also constantly trying to add information about GPUs. So for instance, Gromacs is one of the ones I know that we've come around to document how to use with GPUs. So you can look up there all of the parameters or variables that you should use with the batch system to actually get it to start utilizing GPUs. Another way to double check if the system in question supports GPU offloading is, of course, to just search for CUDA in the list of software. And this command is a nice way to do that. What I've done here is I've asked the module system to list all the available Gromacs instances, but then I said I don't want the width of the list to be more than 80 characters long. And that means that the module software lists them all one by one downwards. And then when I search for CUDA in that list, it only outputs the ones that actually supports CUDA. So here you can see compared to the previous list, because I removed some of the ones for brevity, we actually get one more listed here than what we had before. And in our systems as well, it will be highlighted in red as with this slide here. So it's an easy way. And if nothing comes up, then that means that we don't have a version of that software for GPU offloading. And if you then know that your software should be able to offload and you have some documentation for that, then again, contact us and we'll install the supported GPU software and help you get started using it. So that's a little bit about the modules. Now let's move over to how you would actually specify how to get GPUs within the batch system. So if you just run your slurm scripts as normal, you won't actually get any GPUs. There isn't GPUs connected to all of the nodes, of course, and that's why we need some additional parameters. So the first one that you will always need with the first slurm variable that you will always need to set is to select the right partition. And again, that comes back to not all of our GPU nodes having the prerequisite GPUs. So we need to select only the nodes that have GPUs. But in addition to that, we also need to select how many GPUs we will have. Because if we only select the GPU partition, it will run our code on nodes that have GPUs, but it won't necessarily, or it won't give us a GPU. So we actually have to ask for that specifically. And I've listed all the possibilities of how to ask for a GPU here, or nearly all of them. There is one more, but that's an older variant that is not as popular anymore. And you can ask for -- GPUs. What that means is that I want this amount of GPUs for my whole job. You have then -- GPUs per task, which says I might or might not be launching multiple tasks in MPI parlance, multiple ranks, and I want X number of GPUs per rank. We also have GPUs per node and GPUs per socket. And the last two are probably not all that popular, and you should probably avoid those two in favor of the two first ones. And I would like to highlight this GPU per task because that usually does the right thing always. And let me try to give you an example of why that is. So this is how your slurm script could look if you were asking for GPUs. So hopefully you see some similarities to what we talked about earlier. Here I asked for one task. This task gets 4 CPUs, so it can do multi-threading. It can use OpenMP to divide its work among 4 CPUs. I'm asking for 1 GB of memory, but notice that I'm asking it per CPU. So for this job, I would actually get in total 4 GB of memory. And then lastly, at the bottom here, I've asked for this job to run on the accelerated partition, so on the nodes that have GPUs, and I ask for 1 GPU. And this will work. So our task now has access to 4 CPU threads and 1 GPU. It can do computations with. Very nice. So we can, with this, already start using GPUs. But coming back to what Radwan said earlier in the week about inheriting scripts. If you then just inherited this from somebody else and you wanted to start making changes, maybe you found out that the software you're using, or you want to develop it in a direction that uses MPI, so multiple ranks, you would then go in and change your script to start using 2 tasks instead, but you don't change anything else. And immediately what would happen here is that we just specified 1 GPU, and that's actually what we would get. So these 2 possibly MPI ranks would then just have 1 GPU to share between them. So 2 tasks, only 1 GPU, because GPUs is the total number of GPUs. If we instead used GPUs per task, then this would be correct for both our scripts. So if we ask for 1 task, then we get 1 GPU. But if we then later change our script to ask for 2 tasks, we would still we wouldn't still just get 1 GPU, we'd suddenly get 2 GPUs, and that's probably what we intended. And we see that in most of the software that is already supporting offloading, is that if they support MPI as well, they expect 1 GPU per rank. So I think a good rule of thumb is, if you're asking for GPUs, use the option GPUs per task to get that. Yes, and this is more or less a summary of what I just said. So for MPI applications, you would then ask for X number of tasks. But if you then set GPUs per task to 1, you would likely get the correct amount of GPUs for your task. And that's as well something to keep in the back of your head. If you have a GPU accelerated code, if you then want to add MPI, the not the optimal way, but the easiest way to start with that is to have 1 rank per GPU and assign a GPU per rank, so that they just share the problem and not the hardware. And you can, of course, combine this with CPUs per task if your MPI ranks can do multiprocessing as well. So to summarize that, for MPI, this is probably a good template to use. As you can see, we ask for CPUs per task equals Y. So we have X tasks, and each of those gets Y CPUs. But then with GPUs per task set to 1 and the correct partition, we can have each of our ranks do the correct thing. Yes. So how to get help? It's a good idea to start by checking our documentation. We are always trying to improve our GPU documentation, adding more documentation, adding more documents. If you don't find what you're looking for, always reach out to us. We're always happy to help with tickets and stuff. And know that we at NRIS, and especially the GPU team, can help you get started with GPUs. We can help you look for accelerated libraries. We can help you evaluate if your project will fit for a GPU. We can help you on how to get started. Maybe you want to do some of the development yourself. We can hopefully point you in the right direction. If you've already developed GPU software, we can help you optimize it. And if you have transitioned to GPUs, but think that you could benefit from, for instance, using multiple GPUs, then we can also help you with that scaling out. And on that note, on scaling out, I wanted to just talk a little bit about Lumi on this last slide. And Lumi is a new supercomputer that is being built in Finland in these days. It's European collaboration. So a lot of European nations and Norway are collaborating on buying and building this supercomputer. And what's very interesting for us when talking about GPU is that Lumi is at least the first European system to be fully built around GPU as one of the main ways of doing computation. So of course, all of the nodes on Lumi have powerful CPUs, but Lumi is expected to reach the sort of the benchmark numbers here, mainly using the GPUs. And that's done through collaboration with AMD, where Lumi is actually getting the next generation of AMD HPC GPUs, which are, if the rumors are to be believed, at least, because this hasn't been released by Lumi yet, but we can piece this together by announcement that AMD have made. So each GPU node on Lumi will have 4 AMD MI200 cards. This is the first generation of AMD cards that actually has 2 GPU dice per card. So that means that there are actually, instead of just being 1 GPU on 1 card, there is actually 2 GPUs. Compared to NVIDIA's 40 or 80 gigabytes per device, each of these MI200 has 128 gigabytes of memory, so a lot more memory. And the performance is rumored to be quite a bit more than what NVIDIA is currently providing. So this is a way to scale out your work to multiple GPUs, not just on one node, but as noted in the last point here, these GPUs are directly attached to the interconnect, which means that you don't, to communicate between GPUs on different nodes, you actually don't have to transfer the data from the GPU into system memory and then over the network to the next node, and then again up to the device memory. You can actually communicate directly between the GPUs on different nodes. So Lumi will be the most powerful supercomputers we can evaluate if you're. And that's actually the last slide from this. I used a bit less time on this, so I think maybe we should go back and actually look at the code examples that I intended to show in the previous session. Yes, so let me talk a little bit about OpenMP, CUDA, and Sickle software. And then Sigrun will show us later how to compile these different softwares. So hopefully you can all see my terminal here. I've opened the OpenMP example, and I hope it's large enough. So please shout out if the font is not large enough, and we can make it a little bit bigger. This example here is very, very simple. I just want to create 2 arrays that I want to add together. So we create A and B, which will be our input arrays, and we create C, which will be our output array, and we allocate memory for that. And note that as in regular C, C++, this is just allocated on the host. So currently all on the CPU. The next thing, just to ensure that the compilers don't just remove all of this and make our program do nothing, we actually fill our input arrays with some data. Again, this will be on host as with regular C, C++, but then we come to the interesting part. So what I've highlighted here now is where we're actually doing our computation. But as you've probably noticed, we have a couple of lines above that, which hopefully does some magic for us. So this is how you would use OpenMP to accelerate this code on GPU. You use Pragma to tell the compiler that what's coming next is something that you should process before you continue compiling this code. OMP tells the compiler that this is an OpenMP directive. And then we come to the special directives intended for GPUs, and which are quite new in terms of OpenMP. So target tells the compiler that we would like the next section of code to run on our device, so to run on the GPU. But what if we just add target with nothing else above this for loop, then we'd only run one thread of execution. And what I mean by that is that these 32 threads in NVIDIA parlance would all do exactly the same thing. They wouldn't even share or work on different data. So we need a couple of more things. The next part is this teams distribute. And what this says is that we would like to run not only on our offloading device, the GPU, but we would also like to create multiple thread groups. And that's that teams makes multiple thread groups, while distribute says we want to process all of these elements and give each thread group their separate chunk or slice of this array. So coming back to our presentation, we don't think about just processing one element. We need to think about processing multiple elements. Then this next part is actually needed because we want to have all of the threads in our thread group. So coming from the teams, we want all of those threads to work on individual pieces of memory. So with just target teams distribute, all of the teams, all of the thread groups would still just work on one element at a time. But with the parallel for, we say, give each of those threads in the thread group their individual piece of this array to work on. So with just these 3 lines of OpenMP pragmas, we would actually have this loop be accelerated on our GPUs, and the compiler would then create a GPU kernel for us and run that on the GPU. But as I said, we need to think about transferring memory. And this is just a toy example. So here we've just illustrated how you can move data to and from the device. What we're actually saying here with to is allocate memory on the device and then transfer the linked elements into that device memory. But once we're done with this loop, just throw that device memory away. You don't need to transfer it back because we don't need that data anymore, because we're not changing either A or B. So we just add these 2. Then the from attribute in this map clause tells the compiler that you need to allocate memory for this array, for this C array, but don't transfer memory into this device memory. Just when this kernel is done executing, take all that memory and transfer it back into C. So that's what this from clause does. So this ensures that A and B is on the device, while this from clause ensures that we actually get the results out. So after this for loop is done computing, the correct results will be in the C array, and we've actually done all of our computing on the GPU. And we can then just go ahead and free our memory and exit just as we would do in any other program. So as you can see, adding OpenMP offloading to an existing program might not be that difficult. Of course, as we talked about in the inner workings of our GPUs, there are still a lot to think about, but most of the code will not change. So if we already had these 2 for loops and this array allocation here, we don't need to change any of that. We just need to add this pragmas to get offloading to work. Great. So then let's see how that's done within CUDA. So in CUDA, we are already, you can see some differences. Let's quickly jump over this kernel and come back to that later and see more or less how we allocate data and how we work with that data in CUDA. So to start with, we can see that this program looks slightly similar, but with some changes already. So to allocate memory, we use this library function, CUDA malloc managed. And what that does is it will allocate memory in our pointer. But since it's managed memory, CUDA will ensure that this memory is accessible both on the CPU as well as the GPU. So this one call here actually allocates memory on the CPU and on the GPU at the same time. And what that enables us to do is to work with these A and B, these input arrays, as if they were normal arrays, because to the CPU, they more or less are normal arrays. But then we come to a very large difference, because as we can see here in what I'm highlighting now, this is basically the for loop from before. And this is very strange because we don't see any for loops. We see we're calculating something, it seems, and then we're using this very weird syntax to, it seems, call a function called add, and then we call another CUDA function to do something. So let's get back to the CUDA kernel that we skipped. So a CUDA kernel is what CUDA actually runs on the GPU. And here we see sort of why CUDA gives us more control over our device in comparison to OpenMP, because in OpenMP, where we just added some pragmas around our existing loops, and it seemed to work. But in CUDA, we actually have to say exactly what we want to do. So the first thing to sort of give away that this is a CUDA kernel is this __global __. And that tells the CUDA compiler that this is a kernel that should be callable from the CPU. All CUDA kernels are, or all global CUDA kernels are void. They don't return anything. And then we have the name of our CUDA kernel. So that's what we called below. And then we have these input variables that very much look like normal function input variables. But if you look at the core of this function, we still don't see any sort of for loop. The first thing we do in this kernel is that we calculate our ID. And to sort of give you some idea about this, this is our thread ID. This is our global thread ID, actually. So which thread is this CUDA kernel operating for? We then just have a sanity check in case we launch more threads than there are data to compute over. Check that we actually should access this memory. And then what we do is simply just add A and B into C for this one idea. No for loop, no nothing. And to see how the for loop actually happens, we have to come back to these block size and grid size variables again. So grid size is the number of grids to run, and a grid then contains a set number of thread blocks, so block size. So here what we do is that we say, oh, we want to have 1,024 threads in each thread block. And then we just need to ensure that we have enough blocks to process all of our elements. And then we run that as a kernel. And what happens here is that CUDA will then launch one kernel in one thread, enough to process all of this. And this is where we need to think about how the GPU operates. Here we need to keep in mind that there are 32 threads working simultaneously. You have to think about the memory subsystem, how we can hide latency, and so on and so forth. For instance, I've used a really large block size here. This is a very simple example, so there isn't any need to think about trying to hide latency here. But in larger problems, the more threads that you can run per thread block, the better your utilization of the GPU will be, for instance. So with all of that, we have calculated, we didn't need to transfer anything explicitly to device because we used CUDA malloc. We used managed memory from CUDA. So we can just work on A, B, and C on the host and device. We then ran our kernels and ensured we had enough threads so that everything was processed correctly. And then lastly, because this call is asynchronously run, so on the CPU, it will simply just tell CUDA, okay, run this amount of kernels, call this function, here's the inputs, and then the CPU will just continue processing. So what we're actually telling it here is that, no, stop what you're doing. We actually need to wait for the GPU to be finished before we move forward. And then just as with the CPU example, we free our memory. We need to use a special function for that here, since we used managed memory, and exit as normal. So we can see quite a lot is different here from the CPU example. The initialization, thanks to CUDA managed memory, is very much similar, but then launching our threads and executing on the GPU, very different. And also we had to create our own CUDA kernel or CUDA kernel function to run on the GPU, which is also very different from OpenMP, where the compiler could just do it for us. So let's see Sickle as the last example. And I must apologize for all of these warnings. It's just my editor doesn't understand Sickle. But anyways, I hope it makes some sense. And you can always come back to the presentation and click on the link for these examples, and you will see the source code there, and you can download it and play with it if you want to. So in Sickle, we actually need to start by creating a queue for our operations. And this is basically our interface to the different devices, because Sickle doesn't assume that there is only a GPU that we want to run on, like CUDA does, for instance. And it doesn't try to hide a lot of the complexity as OpenMP does. So Sickle says you need to create a queue, and that is where we will run our operation, and that queue is connected to a device. What we've done here, actually, or what Stig-Rune has done, I should say, because he made the Sickle example and is our Sickle expert, is to just use the built-in logic of Sickle to try to find the best device to run this on. So usually Sickle will prefer GPUs over CPUs and GPUs over other accelerators. For instance, there could be an FPGA connected to our machine. And Sickle we could have a queue for each of these accelerators. But we sort of assume here in this simple example that there is just one GPU connected. Then we allocate memory, very much in the same style as we did in CUDA, but very different from OpenMP, as we said. But here we explicitly use this Sickle Queue so that Sickle knows where to allocate this memory. So it's with malloc shared, it means that Sickle will allocate both for the CPU and for whichever accelerator the queue is connected to. We can then operate on the arrays on the CPU, just as we've done in all of the other examples, or both of the other examples, I should say. So we can see that with Sickle malloc shared memory, we can access it as if nothing on the CPU. But then we can see something strange. And this is sort of the middle ground between CUDA and OpenMP, because what we're seeing here is Sickle's way of interfacing with the device and ensuring that the code is actually compatible with the device that we want to run on. So we say submit. So we want to send something to this queue to actually be run. What we want to run is an anonymous Lambda function in C++ parlance. Within this anonymous function, we want to do a parallel for. So we want to, as in the OpenMP example, we sort of see the for loop in some sense here. And the inputs then to this parallel for is that, well, we want this to be over all of our elements. So we use this special Sickle range to sort of tell the parallel for that we want to calculate on all of these elements. And then we use a second anonymous function to define what we want to do on each element. So this parallel for is then set up to run this Lambda function on each element. And here you can see we see very much the same thing as we saw in CUDA. We just do one thing. There isn't any for loops here because that's handled by this parallel for construct. And then just as with CUDA, submitting work to this queue is asynchronous, so we have to wait for it. But then once that's done, we can interact with the memory as if it was on the CPU all along. And then just as with CUDA, we use a special function to free this special memory before we can exit. And I think that is probably a good place to stop. If there are any questions, we can take them now. And if not, then we can take a break until 11.
Yeah, that's right. Thank you, Jørgen. Is there any questions?
I couldn't hear you, Diana. There is your audio.
Okay. Can you hear me now?
Yes.
Yeah. I was just asking whether is there any questions, please? Yeah, there is one. Seema.
Hi. So I'm curious in this last example, this IDX. Where does that come from? I mean, there is not defined anywhere. Is it some intrinsic thing for Sickle or?
So this is actually the argument to the second anonymous function. So the parallel for is assumed in this example to supply this IDX.
Okay, yeah. So it's part of Sickle.
Yes.
So to speak. Okay. Yeah. Thanks.
So if you haven't seen or haven't used, I should say, C++ anonymous functions, they are quite weird because these square brackets sort of tells us what this anonymous function should capture and how they should capture it. This ampersand tells us that this anonymous function should capture variables as references. This equal sign means that this should capture by moving. As you can see, we don't actually move or copy anything into this, but let's say outside of this, I did if I did j equals 3, and then here I could still do I could still do stuff like this because C++ will then take this J, capture it by value, and then allow me to operate on it in here. So that's the square brackets. What's in these regular brackets is the inputs or the arguments for this anonymous Lambda function. So any caller of this anonymous Lambda function must give me a Sickle handler. And that's the one that I'm running the parallel for on. And the function that I am running on this parallel for is assumed to supply me with an IDX, and that's a Sickle ID. And since we're just launching this kernel or this anonymous Lambda function highlighted here on all of the elements, I just need the ID in one dimension, so the global ID, and that's what we're accessing here.
Okay, yeah, thanks.
Yes.
Jørgen? Yeah.
Short question. How do you compile these things? Do you need? Are you going to show some compiling? Where specifically, what I want to know is there any specific argument you have to pass for vectorization, for example?
Yes. Again, excellent question, Sabri. So Stig Rune will actually show us how to compile these examples and how to run them on Saga. And that's basically to give us a bit more hands-on experience to see this. But yes, so CUDA needs the CUDA compiler, of course, to compile. And then there isn't actually any special arguments to compile. We can just use the CUDA compiler and tell it to compile this special CUDA file. And if you actually see when I open the file, it's actually called .cu, which tells the CUDA compiler that this most likely contains CUDA kernels, and you should compile it as such. For the OpenMP examples, unfortunately, all of the compilers have different arguments on how to tell the compiler that it should actually vectorize these things. But that's something that we have documented on our documentation page on how to use the different compilers and how to run similar programs, OpenMP offloaded programs on our systems. For the Sickle example, you need a Sickle compiler, and on Saga and Betsy, we have the compiler called HipSickle, which is both open source and supports NVIDIA, AMD, Intel, and just CPU offloading as well. So this queue here, if you run on a system that doesn't have any GPUs connected, this queue can also perform this parallel for just on CPUs using OpenMP. And there as well, you need some special arguments that Stig will show us on how to accelerate this, how to tell it that compile this for a GPU, but also compile it for CPU, for instance, all of that stuff. So it's a bit complex, but we just wanted to give you today an introduction to these different technologies. And especially we wanted to show you how they differ, because as you can see for Sickle and CUDA, you can't just take existing code and expect it to run. You actually have to make changes to specialize it for the technologies. For OpenMP, you don't have to do that. But again, with OpenMP, you don't get all of the same functionality as with CUDA and Sickle.
Okay, thank you, Jørgen.